Everybody good? All right, so let's do another problem. This is a classic problem called satisfiability. The input could be some circuit. Input could be some set of constraints, right, on our variables. We're looking for a solution, values to our variables, right? And in 3-sat, it turns out that we're going to have a bunch of clauses, and each clause will have 3 literals, and each literal will either be a variable or its negation. That's 3-sat. So this is an example. Oh, here's this one's a little shorter, but you can imagine some sort of circuit, right? And a solution is a setting of the variables to true and false, right? 0 and 1. And cost of the solution is, hey, let's make it cost 1 if it works, and cost 0 if it doesn't work, right? Or we make it valid if it works and not valid if it doesn't work. Either way, we're looking for a satisfying sum, right? So here in this example, we set x to be 3. We set x3 to be 0. So that makes this true, right? Because it's negated. It makes this false because it's not negated, right? And here the x4 makes that true. And now these are ors, right? So you only need to make one of them true. So that makes each of them true. And these are ands, so you need to make all of them true. All right, everybody buy that? So this is a satisfying assignment. And it satisfies the circuit, right? So our goal, given a circuit, is to find a satisfying assignment. You can imagine how useful that is, right? I'm a robot, and I want to figure out how to get around this stuff and make it out the door. So my solution is going to be a set of variables which tell me what actions I take. And given those actions, right, there's a simple circuit which tells me whether or not I'll get out the door, right? So the way they used to do robot planning before they had neural nets and deep learning is by circuit satisfiability. They're saying, you give me a circuit, you give me, the design a circuit which tests whether a solution is good, right? And then they're saying, give me a solution that works, right? So it's very useful. All right, so if that's my instance, if you've taken, some of you, has anybody taken 1090 from me? Nobody? We did David Putnam for solving these, and this is basically what we're going to do. We're going to do David Putnam. Yeah, but that was easy, and this will not be easy. And the reason that one was easy is because all your clauses had to be horn clauses, and so it was all forcing, and these are not horn clauses. All right, so what we're going to do is we're going to ask our bird the value of some variable. We can ask the bird the value of x1, right? And in this case, you're like, man, that was dumb. That wasn't very useful, right? So let's somehow creatively look at our thing and decide which variable we're going to branch on, right? And when we branch, it basically boils down to asking the bird how to set x3, and we will try both of them. We will try setting the true and false, and that's what I mean by branching, right? And you try both of them, right? And now, if we pretend that she answered false, then we can simplify what we have, right? The x3 sets that to true, so it makes the whole thing true. And here it sets the false. And so this clause is satisfied, so it's gone, right? Right, because we satisfied this clause. So the whole clause is not a problem anymore, right? But on the other hand, this literal is false. So that literal is gone, but we haven't satisfied the clause. So the clause gets shorter, right? So some clauses will be gone, some clauses won't change, some clauses will get shorter, right? right? And then we recursively ask our friend, right? Or dynamic programming, we ask our friend. A friend gives us the solution for everything except the x3. And then we plug the x3, we bring the bird's answer back in, right? So this is a fantastic algorithm, right? What's the problem with it? Yeah, the problem is that we're going to get a big tree, right? We're gonna branch on x3, and then you'll note on when you set x3 to 0, we might branch on x2. While if you set x3 to 1, we simplify it differently, and so you might choose to set it some other way. But any path through this, if you go all the way down to setting all n variables, it's going to be a depth of n, and so we're going to have it 2 to the n. And when you, in fact, if you set all the variables, you get down to an assignment, right? So we don't want it, right? So that's no good. Now, hopefully you don't have to do this whole tree, right? Hopefully you set a few things and it's simplified enough that you know it's satisfied or you know it's not satisfied, right? But that's, in the worst case, that's not the case. You have to go pretty far down, right? All right, so in dynamic programming, what we do is we find out what's the whole set of subinstances that might arise, right? And try to figure out that whole set of subinstances. All right, so if this is our instance, and I just made a really simple thing here, right? I got x1 and x1 and y1 and x2 and y2, right? So nice symmetric example. And right, so then I ask, what are the subinstances, right? So is this a subinstance? I guess I'm going to say here, if I commit to these things, right? I commit to everything, right? Everything except x1, then I don't know. That wasn't very clear. So here's what we're going to do. Take any for each of these clauses, you're going to choose to either drop the clause or keep only the x part, right? So that's going to give you a subclause because either you drop the whole thing or you keep the x. So that'll give us 2 to the n. If we have n of these clauses, it'll give us 2 to the n different clauses, subclauses, right? Now, then, so here's a particular one, right? Where I kept the x and I dropped these 2, right? But you can imagine any such subinstance. And how do we get it? Well, if I set y to be 0, then it doesn't satisfy this clause, so we keep the x, right? But if I set y to be 1, then it satisfies this, so we use the whole clause, right? And so by the different settings of our birds, different branches, on different branches of the tree, we're going to have different subinstances. And we're going to have an exponential number of different subinstances. Does that make sense? And in this example, I mean, this example is clearly easy. And what you should have done is you should have branched on x1 and then branched on y1 and then branched on x2 and then branched on y2. And it would have been easy, right? But the problem is that for an arbitrary circuit like this, you do get an exponential number of subinstances. So this is saying, but now we're saying, okay, we're going to have this big tree, but maybe we can prune off some of its branches. And how do we prune some of its branches? Like suppose this was our instance, and in some ways, this, you'll note here, this clause here is like one of your horn clauses, right? It forces, this forces X to be false, right? And that effectively kills one of the trees, right? And similarly, what does this do? Makes it impossible. It kills off both of your trees, right? So that's how you can prune. And so here's the Davis-Putnam algorithm, which is I'm given C is some set of constraints, and I'm trying to find something that, I don't know if you can even read this, but it's basically says you choose some variable to branch on, and you try K, setting it to 0, say setting it to false, and you simplify and recurse. Right? Everybody good? Here's another problem, which is you have a chessboard, right? And you want to know how many queens can I put on it so that no queen can kill any other queen, right? So you can't have two queens in the same row or same column or the same diagonal. And if you were to do the, I try all the places to put the queen on the top row, and then I try all places to put it on the second row, right? Same sort of Davis-Putnam's kind of thing. You would think that, I mean, it could grow to all possible solutions, but in fact, it runs very fast, right? Because as soon as you put no. What on an 8x8 board, it runs very fast because as soon as you put a couple queens on, it really eliminates things. But I had this as a test question once, and you can argue that the running time is still something like 3 over 3 to the end. And so you don't eliminate enough. Anyway, that's what we've said a couple of times already. That's what we've said a couple of times already. That's we've said, you know, I think we're good.